Hi folks, we're going to take a look at the solutions to the October 20 quiz. Okay, so let's start with number one. So they give us this function, which looks like it's a transformation of log base 3 of x. So they're asking us to choose one single point, okay, other than 1, 0, and show how it's transformed to a point on f. Okay, so obviously the easiest point to use would be 1, 0, but we're going to choose another one. So let's pick some other point on y equals log base 3 of x. And I guess the easiest one to choose is when the exponent is equal to 1, 3 to the 1 is equal to 3. Okay, so when x is 3, when y is equal to 1. So this is what we're going to transform. Okay, but of course, anytime we're dealing with transformations and we see a coefficient other than 1 in front of x, we know we have to factor it out. Okay, so we'll rewrite this here as y equals -2 log base 3 of 2 times x minus 3. Okay, and this is going to allow us to correctly identify our transformations. Okay, so let's see what happens to this point, and let's start with the x values. Okay, and we know that here this factor of 2 is going to have the opposite effect. So instead of multiplying 2 to 3 is going to be divided by 2. And then again, opposite to what we see, we're going to be adding 3. Okay, and let's see what happens to the y value. Well, the y value, there's just one transformation. We just have to multiply the y value by -2. Okay, so all we have to do now is calculate this here. So here we have 3 over 2, 1.5 plus 3 will be 4.5 or 4.5, and then this just becomes -2. Okay, so again, steps here, determine your point. Okay, write your equation in the correct form in order to be able to identify the correct transformations, and then apply the transformations to the x and y components, the ones that apply to it. Okay, let's move on to number 2. So here they're asking us to evaluate this logarithm here. I mean, they say simplify, but best case scenario is if you can actually write as simple a number as possible that's equivalent to this number here. Okay, now the only way to evaluate a logarithm without a calculator is to somehow write the input as having the same base as the base of the logarithm. Okay, and that looks doable because our base is 1/2, and we see a 4 here, which is actually a base to a power, because cube root of 3, or sorry, cube root of a number is just the same as that number to the exponent of 1/3. Okay, so that'll be our starting point. This changes cube root to exponent 1/3. Now from here, how do we write 4 as a power with base 1/2? Well, again, since this is an integer and that's a fraction, we know we're going to need a negative exponent. Okay, so if we take 1/2 to the -1, it'll give us 2, and then we need to square it to get 4, so that's why we need -2 here. And of course this is all to the 1/3. Let's use our exponent rules to simplify. So this is 1/2 to the -2/3. And now we can evaluate the logarithm, because here we just have inverse functions. Okay, so they essentially cancel each other out. So I'm just left with my original input here of -2/3. Okay, so again, when you need to evaluate a logarithm without a calculator, the way you need to figure out, the way you do that is to figure out how you can have a power with the same base as the base of the logarithm. Okay, so let's move on to number 3. Okay, so here we have an exponential equation because we've got variables in the exponents, and this is sort of our outlier. Okay, because it's not easy to write this as a single power equal to some number. Okay, so the method we use for doing this, because we still need to get those variables out of the exponent is to take a logarithm of both sides, as we normally would do, except instead of picking log base 3 or log base 5, is we use sort of a third logarithm, in fact the one that our calculator can work with. Okay, so the suggested method for solving these is to take log base 10 of both sides. Okay. Now the reason why that's useful is because you can still use the ski-slope rule in order to bring these exponents down. Okay, and since everything's in terms of log base 10, you can then use your calculator to check your answer or to get an approximation if you need one. Okay, so step number 1, take log of both sides. Now let's bring down the x minus 2. So you have x minus 2 times log of 3, and here you've got x times log of 5. Okay, but now this is just a simple linear equation. Okay, it does have these odd coefficients. Okay, but in the end, it's just a linear equation. So how do we deal with these? Well, we simplify both sides, bring all the x's to one side, numbers to the other, and then solve. Okay, so first thing I have to do is distribute the log 3. So I'm going to write this as log 3 times x. So again, log 3 is just a number, just the coefficient of x, minus 2 log 3. Okay, and here I'll just rewrite this as log of 5 times x. So just we keep that pattern of writing the coefficient in front of the variable. Okay, so now we bring all the x's to one side. So here we have log 3 times x minus log 5 times x. And then we'll bring that to the other side, which will be positive 2 log 3. Okay, here, this is just a subtraction of like terms. How does one subtract like terms? By subtracting their coefficients. So I have to subtract log of 3 minus log of 5 times x. You can also think of this as factoring out the common factor of x. Okay, it's equivalent to doing what we did. Equals 2 log of 3. And now we can solve for x by just dividing its coefficient. So we have 2 log 3 over log 3 minus log 5. Okay, and we can simplify this a little more because this 2, which is a coefficient, can be brought up using the ski-slope rule, which then becomes log of 3 squared, which is 9. And then here we can bring these two logarithms together because the difference of a logarithm is the same as the logarithm of the quotient, so 3 over 5. Okay? Now, there's other ways to solve these problems. Okay, so in the end, you can either use your calculator to see if your solution is the same as mine, or you can do the algebra to show that they're equivalent. Okay, but just to recap, this is that special scenario where we can't have one exponential expression equal to some number. So instead of taking the logarithm of whatever a base we're working with, we just take log base 10 of both sides, bring things down, and work with it as whatever equation you get. In this case here, turns out it was just a linear equation. Okay, so let's move on now to the other page. Okay, so the first thing they ask us to do here is to simplify and state the restrictions on the variable. Okay, so here I see a bunch of logarithms that all have the same base. They all have base 10. Okay, and they're all additions and subtractions. Okay, so the way in which we can bring them together is to just use our exponent rules. Now, if I had any other coefficients, say a 2 here, I'd just use the ski-slope rule first. But here, all the coefficients are either 1 or minus 1. Okay, so I can bring these all under one logarithm. Now, you could do it in 2 steps, but here I'm going to do it in 1 step, because here, the sum of 2 logarithms is equivalent to the logarithm of the product. And then once I've simplified these two, subtracting a logarithm is equivalent to the logarithm of the quotient. So I'm just going to be dividing by x squared minus 9. Okay, which of course can be rewritten as, okay, let's try to simplify if we can. We realize, there's a common factor of 2. Okay, so remember, don't just think about difference of squares and trinomial factoring or grouping. Don't forget good old common factoring. Okay, and here when we factor the denominator, we have x plus 3, x minus 3. Okay, and of course these reduce, so I'm just left with log of 2 times x minus 1 over x minus 3. Okay, and there's my simplified expression. Okay, now we have to find the restrictions in the variables. So this is where you have to be careful, because yes, there's a restriction of, the input not being able to be equal to 3, or the x values can't be 3 or negative 3, because that'll give us a 0 in this denominator. But remember, it's much more than that. Okay, we actually need all of these expressions to have positive inputs. Okay, so it's very important that we have to look at the original equations or original expressions to determine our restrictions on the variable. Okay, so let's take a look here at 2x plus 6. Okay, so let's see where 2x plus 6 is positive and negative. Okay, well, this again can be written as 2 times x plus 3. So this is a line. Now notice here, remember, these are just polynomials, so I'm going to, use the fact that I can draw them easily. Okay, so here it has an x-intercept at negative 3. The slope is positive, so I know that this is going to be greater than 0 for all values greater than 3. Okay, let's look at the x minus 1. So notice here how I'm dealing with them individually, because I need to make sure that all 3 are satisfied. So let's look at the x minus 1. Again, let's draw the line. This has a 0 at 1. Okay, this is only positive for numbers greater than 1. So forget about this portion here. While, say, negative 2 is an okay input for the first one, it's not an okay input for the second one. Okay, and now let's look at x squared minus 9. Okay, well, here we realize that x squared minus 9 is positive less than negative 3, which I'm not going to consider because it doesn't fit with the other two, and greater than positive 3. Okay, so again here, between 1 and 3 was okay for the first two expressions, but not for the third. So the restrictions on the variable, okay, is that x has to be strictly greater than 3. Okay, because those are the only values that are going to make all 3 original expressions positive. Okay, so let's move on to number 5. Okay, so here we see again an equation with exponential expressions that have variables. So we have an exponential equation. Okay, but this is not quite the same as what we had in number 3, because here when I look at 3 to the x and I look at 9 to the x, I realize that I can get both of these into with the same base, because here 9 is just equal to 3 squared. Okay, now I'm not quite there yet because I have 3 squared. I don't have 3 to the x. But remember, third exponent law says that I can multiply these two exponents, and since multiplication is commutative, I can rewrite this expression as 3 to the x squared. So hopefully at this point here, you start to recognize this, that as soon as you see this type of scenario, that you realize, oh yeah, 3 to the x, 3 to the x squared. Okay, but writing it in this way, right away I start to see that I've got something that looks quadratic. So right off the bat, I know I'm going to bring my 6 to the other side equal to 0, so I get something that looks like a quadratic equation. So I'll use the old trick again. At this point you may be able to solve these problems without doing this change of variable, but it's a good idea just to be sure. So I'm going to rewrite this now as z squared minus 1z, okay, minus 6 equals 0. And this is really nice because it's factorable. So it's z minus 3, okay, and z plus 2 equals 0. So z is equal to 3, or z is equal to negative 2. But of course it's not z that I'm interested in, it's x. So I'm going to replace this by 3 to the x, and replace this by 3 to the x. And now this one works out really easily because there's just 3 to the x equals 3 to the 1, so x has to be equal to 1. Okay, or 3 to the x has to be equal to negative 2, but then I realize that this is an expression that is always positive, so can never be equal to negative 2. So we have to eliminate that solution. So in the end, all we have as a solution is x equals 1. Okay, now let's move on to the last question here. Okay, so here we have a logarithmic equation. Okay, and in the same way that for an exponential equation, my goal is to eventually reach this stage where I have a single exponent, a single power equal to some number, so I can solve it. In this case here I was lucky I didn't have to use logarithms, otherwise by using logarithms. Well, we want to do a similar thing here, is we'd like to eventually write this to have a single logarithmic expression that's equal to some number. Okay, and we'll see what we can do with that. So I look at my left hand side and I see I've got two logarithms that are being subtracted, which is the good news because hopefully I can use one of my logarithm laws. The problem is I don't just have log of a minus log of b. I've got this 2 in front. So it doesn't quite fit my log rule. But luckily we have the third logarithm law that allows us to bring this 2 using the ski slope going backwards and rewrite this first expression as log base 3 of x minus 1 squared. Okay, minus log base 3 of x plus 1. Okay, and now I have a scenario in which I can use the second logarithm rule because I've got a logarithm minus a second logarithm. And so now I can apply that. So log base 3, and this becomes x minus 1 squared over x plus 1, and that's equal to 2. And now we have the format that we need, because once we have a single logarithm equal to a number, I can now rewrite this in exponential form. Okay, so 3 exponent 2 is equal to x minus 1 squared over x plus 1. Okay, and what I'm left with is just now a rational equation. Okay, and a fairly simple one here. So the way we solve rational equations is we multiply both sides by the lowest common denominator. In this case here it will be x plus 1. So this is 9 times x plus 1. So on the left hand side I've got 9x plus 9. And then here I've got x squared minus 2x plus 1. And so now I just have a quadratic equation, which is nice and easy to solve. So let's get 0 on this side here. So we've got x squared, so negative 2 minus 9x, so minus 11x. And then 1 minus 9 is negative 8. Okay, and taking a quick look, I can see that this is not going to be factorable. So let's go straight into using the quadratic formula. So negative b, so that's going to become positive 11. Plus or minus negative 11 squared is 121 minus 4 times 1 times negative 8 all over 2. So here what do I have? I have 11 plus square root of 121 plus 32. So 51, 53, so 153 over 2, or 11 minus square root of 153 divided by 2. And here are our two answers. Okay, now it would be tempting to stop here. Okay, but remember, these are the solutions to this quadratic equation. we actually need to make sure that these satisfy the original equation. Okay, so that means the inputs to the logarithms. Okay, hopefully nothing went wrong because my computer just shut off, so hopefully this keeps going. Okay, so let's go back here. So we have these two answers, but they have to satisfy the original logarithmic equation. Okay, now this one seems okay because I have 11 plus some positive number over 2. This is definitely bigger than 1. So when I put it into this logarithm here, I'll get a positive number, I'll get a positive number, no issue. This one's okay. This is the one that worries me because square root of 153, well, square root of 144 is 12, so this is definitely going to be a negative number. And a negative number minus 1 is still negative, so we have to eliminate this. This is what we call our extraneous root. Okay, so just to recap, logarithmic equation, your goal is to get it into this form where you've got a single logarithm equal to a number, so that then you can transform it to exponential form, and from there use methods for solving rational or polynomial equations to get your answers. But very important, whatever you get, you have to make sure satisfies the original equation. Okay, and that's it for this quiz.